Hello everyone and welcome to Sky Scholar. Today we resume the analysis of planetary nebula. In our last video on the subject, it was emphasized that the spectra of these objects are dominated by forbidden emission lines, the most powerful of which usually originate from oxygen-3 at 495.9 and 500.7 nanometers. Here is a more exhaustive list of the types of atomic and ionic emissions observed in planetary nebula. As before, square brackets are used to designate species giving rise to forbidden lines. We also reviewed Bowen's idea that planetary nebula must be hypodense in order to account for the presence of these forbidden lines. This claim was rapidly accepted in astrophysics and dominates current thought relative to such objects. However, the idea that planetary nebula must be hypodense was countered by Gauzit in 1943 when he highlighted that the only forbidden lines observed in the laboratory at the time were detected under relatively dense atmospheres. This was especially true relative to the detection of the auroral emission lines from oxygen-1 by McLennan. Modern inorganic chemistry has even more to add relative to forbidden lines when examining the well-known luminescence of rare earth elements within host crystals. Such ions are known to undergo forbidden transitions. These forbidden transitions are used extensively throughout inorganic chemistry and in the commercial development of LEDs, phosphors, and lasers. Clearly, highly rarefied atmospheres are not required in order to have emissions from forbidden transitions. Here is what Sato et al. Have to say on the subject of forbidden transitions in lanthanide-containing crystals. Electric dipole transitions within the 4F shell are strictly forbidden because the parity does not change. However, the forbidden transitions are actually observed due to the fact that the interaction of the rare earth ion with the crystal field or with the lattice vibrations can mix states of different parity into 4F states. Coupling of 4F electrons with transient dipoles induced in the ligands by the radiation field leads to an amplification of the even parity multipolar transition amplitudes for transitions within the 4F shell. These transitions are called induced or forced electric dipole transitions. Here is another quote along the same lines. Laporte's parity selection rule implies that states with the same parity cannot be connected by electric dipole transitions. As a consequence, F to F transitions are forbidden by the electric dipole mechanism. However, when lanthanide ions undergo the influence of a ligand field, non-central symmetric interactions allow the mixing of electronic states of opposite parity into the 4F wave functions, which relaxes the selection rules and the transitions become parity allowed. They are called induced or forced electric dipole transitions. Herein lies the problem for the accepted theory of planetary nebula. The most important forbidden transitions on Earth today occur within crystals, and the responsible agent for triggering the transition is the lattice. The presence of forbidden transitions in solids bring into question the hypodense conditions currently advanced for planetary nebula. Forbidden transitions can indeed occur when condensed matter is involved, because interaction of an ionic species with a lattice can distort its electron cloud, generating forced electric dipole transitions. Now let us return to the list of some of the most common species seen in the spectra of planetary nebula. How does modern theory account for the transitions from these species? First of all, as we just learned in our last video, it begins with the assumption that planetary nebula are highly rarefied or hypodense. This comes from the classic paper by Bowen and is used to justify the presence of the forbidden lines. Then, in order to produce all these ionized species, it is assumed that a central star within the planetary nebula emits UV radiation. Typically, this central star is said to be extremely hot with temperatures ranging from 30,000 to 200,000 Kelvin, as one can learn in this paper. It is then said that the emitted UV radiation can ionize hydrogen and helium atoms within the nebula, releasing free electrons in a process known as photoionization, as one can learn here. The ejected electrons are then used to ionize other atoms. The ions produced then recapture electrons, and this recombination leads to the emission lines observed. As a result of the photoionization process, planetary nebula are said to have electron temperatures of 7,000 to 20,000 Kelvin. Here is a quote. Many years ago, Menzel and Aller showed that for a photoionized nebula of normal chemical composition, TE could not much exceed 20,000 Kelvin, no matter how hot the exciting star. Yet as a result of such statements, problems remained, as the production of some ions, especially species like argon-5 and neon-5, required much higher energies than could be achieved through the simple bombardment by electrons once ejected from hydrogen or helium by UV light. As a result, still another method was proposed to produce ions such as argon-5 and neon-5. Shock waves within the nebula must now provide the answer. Again from Aller et al. Shock effects may influence only a relatively small portion of the emitted volumes, but have an enormous influence on the intensities of the lines of high excitation, which originate in zones far hotter than predicted by any photoionization theory. Of course, they could never measure the real temperatures in such zones. They simply infer that they must be there because they have no other means of accounting for the neon-5 and argon-5 transitions. New mechanisms have thus been introduced for heating nebular material, including shock waves. But if such waves really exist, why not produce many more highly ionized species? Then there is the problem of why only certain atoms are producing emission lines and why the relative abundances do not seem to agree with what might be expected, as different methods of calculating elemental abundances yield different answers. Astronomers must hypothesize that certain atoms are much more volatile, such as neon and argon, while other atoms become sequestered by interactions with dust particles within the nebula. The problems with all these ideas are self-evident. First, it is impossible to account for uniform excitation of ions throughout a nebula, which might extend fractions of light years based on the emission of a single star. That should result in more centralized ionic emissions, not one that extends over the entire structure. So clearly, the mechanism which results in emission must be local and independent of central star arguments. Secondly, it is known that molecules such as carbon monoxide have been detected in planetary nebula, as one can learn in this paper. Rotational analysis reveals excitation temperatures on the order of only 11.7 Kelvin for this molecule in this setting. In fact, there are now many planetary nebula where the carbon monoxide lines are clearly seen, and they all point to lower temperatures. Next, have a look at this figure of the spectrum of Planetary Nebula NGC 7027, the Magic Carpet Nebula. Note the two superimposed blackbody lines. The peak wavelengths of these two blackbodies correspond to about 10 and 30 microns respectively, which translates to temperatures of nearly 300 and 100 Kelvin respectively. Again, this is much lower than the 20,000 Kelvin or greater electron temperatures hypothesized by modern theory to result from photoionization. Even more concerning is the known presence of fullerenes in planetary nebula, as can be noted in this figure. Fullerenes are cage-like molecules like C60, which are known to be extremely sensitive to destruction by UV light, as one can learn in these two papers. As a result, if fullerenes are present in planetary nebula, how can the photoionization scheme required to account for ion formation be valid? In fact, naturally occurring fullerenes are not found on Earth, precisely because they are destroyed by light, as mentioned here. Thus, one cannot simultaneously argue for an environment so UV harsh that photoionization of hydrogen and helium can readily occur, while at the same time report that strong fullerene lines are present in the same object. It is well known that UV light is destructive to many complex organic molecules. Just examine this quote from NASA relative to the discovery of an even simpler molecule within the Orion Nebula, CH3+, or methenium. Typically, UV radiation is expected to destroy complex organic structures, in which case the discovery of CH3+ might seem to be a surprise. However, the team predicts that UV radiation might actually provide the necessary source of energy for CH3+ to form in the first place. Talk about twisted arguments. In order to preserve the model of photoionization in planetary nebula, it is now argued that photoionization permits the formation of organic molecules which on Earth are known to be destroyed by photoionization. In any event, one thing is clear. Chemists will view the presence of fullerenes in planetary nebula as a sure sign that UV photoionization does not play any significant role in such objects. Furthermore, the presence of organic molecules in planetary nebula point to densities sufficient for chemical reactions to take place, not ultra-rarefied conditions. As a result, the accepted theory of emission lines in planetary nebula loses the only means to account for the ionic transitions observed in such objects. Relative to the theory of photoionization in the nebula, the discovery of fullerenes should have caused the astronomers to scream, "Houston, we've had a problem here." But not one word of doubt was ever expressed to the outside world. Furthermore, in the laboratory, fullerenes are made in environments often devoid of hydrogen, typically by running an electric arc through graphite electrodes in a helium atmosphere. Their presence in planetary nebula, thought to be rich in hydrogen, should therefore come as a shock to everyone. In the fullerene molecule, one requires isolated carbon atoms, and it is difficult to envision the synthesis of such a molecule in a hydrogen-rich environment unless a specific, non-random setting is involved in its synthesis. In any event, one thing is clear: planetary nebula are rich in chemistry. The goal is now to understand the key reactions. As such, let us begin with the transitions that are usually amongst the most powerful in planetary nebula, namely the forbidden transitions from oxygen 3 at 495.9 and 500.7 nanometers. Ideally, these transitions should be accounted for in a single step, not governed by extreme temperatures, but only by chemistry and the local environment. In order to solve the problem, condensation reactions will be invoked. It is important to keep in mind that whenever condensation occurs, the problem is to get rid of the heat. Relative to planetary nebula, this will be done by emitting photons, and that is what will account for the transition lines. But what condensation reaction can possibly account for the presence of oxygen 3 forbidden lines? In order to solve this riddle, let's consider the most important oxygen-containing molecule, namely water. Water is ubiquitous in the universe, as one can learn in this paper. Consequently, we must imagine that water is involved in condensation reactions similar to what was described in this paper and video when considering chemical reactions in the chromosphere. Of course, in order for such reactions to occur in the nebula, one would need to have condensed forms of hydrogen present. I refer to these as condensed hydrogen structures, CHS. Given that the nebula are likely to be produced by shedding the external envelopes of condensed hydrogen layers on stars, the premise is reasonable that condensed hydrogen structures exist in planetary nebula. Now consider this reaction. Imagine that when water is utilizing condensation reactions, two hydrogen atoms are transferred to a condensed hydrogen structure. During this condensation, each hydrogen atom takes not just its one electron, but two electrons away, As a result, each hydrogen atom is taking with it an extra electron. That is why there is a little minus sign as a superscript. Now, if these condensation reactions take place, the initial product would be oxygen plus 2 in excited state. That is what the little superscript asterisk to the left of the oxygen plus 2 signifies. Now, oxygen plus 2 is the same as a third ionization form of oxygen, or oxygen 3. One of the electrons in the oxygen plus 2 has been promoted to a higher energy level by the condensation process, and the heat associated with condensation has now been transferred to this electron. Next, in order to get rid of the heat of condensation, this excited oxygen 2 electron could then undergo a forbidden transition in order to relax back to the ground state. The end result of the reaction is an emission line from oxygen plus 2, which once again is known as a third ionization state of oxygen, or oxygen 3. The central aspect of this problem is that condensed matter is present during these reactions. As a result, if the oxygen 3 is still interacting with this material, even slightly during emission, then the forbidden transition might not only be facilitated, but selected. A forced electronic dipole transition could take place, as we saw earlier with the lanthanides and crystals. This condensation reaction is similar to what was observed in the condensed reactions of silver clusters on Earth, as we learned in this video. In that case, an excited silver atom was ejected from a larger cluster assembly following condensation. In order to get rid of the heat associated with condensation, the excited silver atom then emitted a photon and relaxed back to the ground state. Note that such processes are essentially independent of the environmental temperature. What matters is the chemical process, as it is governing photon emission. There is another simple way to obtain forbidden transitions in oxygen 3, and that would involve starting not with water, but with the hydroxyl cation, which is known to also exist in astrophysics, as seen here. This would lead to this set of reactions. Using these ideas, all the oxygen lines in planetary nebula could easily be explained as products of condensation reactions, whereby hydrogen atoms and electrons are transferred to condensed hydrogen structures. The hydroxyl molecule, which is also known to exist in astrophysics, could easily come into play to introduce the oxygen 1 or oxygen 2 lines, depending on whether 1 or 2 electrons are transferred along with a proton during condensation. In this light, consider that the water cation H2O+, or water which has lost 1 electron, has also been detected in astrophysics. This could account for the presence of oxygen 4 lines in planetary nebula, as seen in this reaction. Similarly, the hydronium ion, or H3O+, is expected to be amongst the most ubiquitous in the universe. Given this fact, the emission lines from oxygen 5 could easily be explained, as one can note in this reaction. In this regard, note that the existence of a particular line has very little to do with temperature, as chemistry and condensation now dominates. Given that the reactions with water and its derivatives can so elegantly account for the emission lines in planetary nebula, similar reactions could be applied with nitrogen. For instance, when examining this set of reactions, one will note that the needed precursors exist in an astrophysical context. So many lines can be produced, and all using the same principle of condensation followed by emission. Much like nitrogen, similar reactions could take place with carbon hydrides, and many of these are known to exist in astrophysics. For instance, the emission noted above in the methylene cation could be produced by this reaction. This is also the case both for sulfur and silicon. Of course, hydrogen emission lines themselves would involve very simple reactions such as the following. In this case, a single hydrogen atom would be transferred. This could potentially lead to an understanding of all the hydrogen emission lines, although other processes may also well take place. But now we get to the really interesting atoms. Let us begin with chlorine. One can easily envision reactions involving hydrogen chloride and the hydrogen chloride cation, especially when the latter is known to exist in the interstellar medium. Such reactions could account for emission lines arising from chlorine 1, chlorine 2, and even chlorine 3. But what about chlorine 4? Well, it turns out that this molecule, known as chloranium, is the electronic equivalent of water. The molecule actually has a name, but has yet to be observed on Earth. Still, it could well be present in the nebula, and if so, would easily account for the presence of chlorine 4 lines. As the electronic analog of water, chloranium simply should not be ignored, as it may play an important role in planetary nebula. But there is more, namely the problem of the missing helium-1 transitions in the ultraviolet spectrum of planetary nebula, particularly the allowed line at 58.4 nanometers and the forbidden line at 62.5 nanometers, both of which are indicative of transitions from the 2p to the 1s orbital as follows. However, these important lines are simply not present in planetary nebula. For instance, in 1980, a professor from Cambridge, J.G. Ferland, argued that the species leading to the missing helium-1 line in the UV spectrum of planetary nebula must be magically destroyed by photoionization. These arguments must be considered as wishful thinking because the helium-1 recombination lines are clearly present in the visible as seen in these spectra. One cannot simultaneously observe the recombination lines of helium-1, which populates the 2p orbital, and argue that the species leading to the UV lines from the same orbital are now being destroyed. As a result, the photoionization destruction of the species responsible for UV lines in helium-1 is simply not sound. In this regard, have a look at these two orbital diagrams for helium-1. The solid yellow lines depict the allowed emissions which have been reported in the Williams University spectral collection. The solid red lines depict the forbidden transitions observed for helium-1. The broken yellow lines report the UV transitions, which to my knowledge are not observed in helium-1 within planetary nebula. That was the claim by Ferland. Note the commonality of the 2p orbital for the observed and unobserved transitions as mentioned above. The lines which are not observed arise from the same species which Ferland claims are destroyed by UV photoionization. Yet it is not reasonable to conclude that photoionization can completely destroy one group of lines but not affect another. And again, if the species leading to UV lines from helium-1 are being destroyed by UV photoionization, then why are the fullerene lines present? Something much more subtle must be happening, as we shall soon see. Next, let us place on the diagram several more allowed and forbidden transitions for helium-1 in the optical range. One can find these lines in this paper, and there are many, many more. These are also known as recombination lines. Where are all those lines if it is true that random recombination of electrons with helium ion are responsible for the emission lines observed in planetary nebula? If the claims of the astronomers were correct, then these lines should also be seen. This clearly indicates that the processes involved are not random. Specific spectral lines are being selected, and there must be a reason. In any case, the absence of helium-1 UV lines in planetary nebula demonstrates that nothing is random here. In this video, you might recall that I highlighted the presence of missing helium transitions in the chromosphere and asserted that chemical selection was taking place in this region of the Sun. Nothing is achieved by chance, neither in the chromosphere nor in the nebula. Rather, we are dealing with inorganic chemistry. But how could this be? How could we be dealing with inorganic chemistry? After all, we are examining transitions from a noble gas, namely helium. So how can one possibly argue that helium is involved in condensation reactions? After all, everyone is taught in freshman chemistry that the noble gases don't want to participate in chemical reactions. In reality, that analysis is much too simple, as in advanced courses, it is apparent that even the noble gases get to participate in chemistry. So let us consider helium very carefully, as it is the first of the noble gases and as its chemistry is the most fascinating. The helium hydride cation is known to exist not only in the laboratory but in astrophysics. The presence of the helium hydride cation could easily account for all the helium-2 emission lines observed in planetary nebula. When a hydrogen atom is deposited onto a condensed hydrogen structure, this leaves behind a helium plus ion, or helium-2, in excited state, wherein helium has lost an electron. As the helium-2 relaxes, the associated lines are thus produced. Next comes the hard part. Let us return to our orbital diagrams. How are the selected helium-1 lines produced in the optical, and why are they not there in the UV? For instance, the helium-1 optical lines might involve transitions of an electron from the 3d orbital to the 2p orbital. Conversely, the UV helium-1 lines involve a transition from the 2p orbital down to the 1s. In order to understand why all of this is happening, one must first recognize that helium hydride does not exist on Earth in the ground state, but only as an excimer. What are excimers? Simplistically, they are molecules that only exist in excited states. To form an excimer, one must first begin by promoting a helium electron to an upper energy state, as seen here. One electron moves from the 1s shell up to the 2p shell, for instance. At that point, if helium makes a molecule with hydrogen, 2 electrons will move into the sigma bonding molecular orbital, one from helium and one from hydrogen. Now, what if the helium electron, which had been promoted to a p orbital in the atom, enters a pi molecular orbital? This results in an excimer because in the ground state of the molecule, the lone helium electron should be contained in the anti-bonding sigma orbital. But the lone helium electron does not enter the anti-bonding sigma orbital of the ground state. It remains promoted and enters a pi bonding orbital. As a result, one of the electrons in the helium hydride molecule is already excited and an excimer has been formed. The ground state molecule simply does not exist. So now you have a molecule with an excited upper electron, an excimer. Next, think about what's happening if the helium hydride excimer is involved in a condensation reaction. When the hydrogen atom is deposited onto the condensed hydrogen structure, the helium is released, but now the electron which was in the pi bonding orbital is promoted to an even higher atomic orbital, like 3d for instance, to account for the heat of condensation. We can denote this with a double asterisk to the right of the helium-1 symbol. As a consequence, when the resultant helium atom finally relaxes after depositing hydrogen, the transition is from 3d to 2p. Since the helium atom has not fully relaxed back to the ground state, then it is still denoted with an asterisk. Note that because the species making the transition arose from an excimer, the 2p to 1s transition never occurs, precisely because no electron was ever allowed to remain in the 2p shell following condensation. That is why the helium-1 lines in the UV involving 2p to 1s transitions are never observed in planetary nebula. This is a sure sign of chemical selection. Furlan's idea that the lines are not seen because they were destroyed by photoionization does not make sense, because the recombination lines from helium-1 are clearly present in the optical. If optical lines from helium-1 are present, then so must the UV lines, if the process was completely random and governed only by UV photoionization. In this regard, note how the recombination lines are actually populating the 2p shell. Yet the UV transition from 2p to 1s does not occur. The only explanation must be that chemistry is at play here. Once helium-1 has an electron in the 2p shell, it immediately reacts with hydrogen and forms the helium hydride excimer. As a result, the atomic transitions from 2p to 1s are prevented from occurring. This points to the fact that the hydrogen density is elevated in planetary nebula, because if it was not, the excimer would not be formed as quickly, and one might expect to see the UV transitions of helium-1. So the absence of helium-1 UV lines points elegantly to chemistry and to the fact that planetary nebula are not highly rarefied. That is why we do not see the helium-1 UV lines in such objects. Nothing is random here. An appreciation of laboratory inorganic chemistry provided the answer. Now this is all well and good relative to accounting for the helium-1 and helium-2 emission lines, but what about emission lines from neon and argon? Those are also noble gases. Surely one cannot argue that chemistry is involved here as well. How can one possibly account for the formation of neon-5 and argon-5 lines using condensation reactions? It turns out once again that chemistry comes to the rescue. Just consider this set of condensation reactions. Both neonium, namely NEH+, and argonium, ARH+, are known to exist, and neon hydride and argon hydride are also known to exist in the laboratory as excimers. It is easy, therefore, to support the formation of emission lines from neon 1 to neon 3 and argon 1 to argon 3. Furthermore, the neon dihydride cation and the argon dihydride cation are also known to exist, and that could account for this set of reactions, including the formation of emission lines from neon 4 and argon 4. But what is most shocking is that the trihydrogen cation of argon, namely ARH3+, is known to be stable. That would lead to our desired argon 5 emission lines. The neon 5 emission lines could occur through a similar mechanism, although the trihydrogen cation of neon has weaker internal bonds than its argon analog. It is also clear that the reactions presented herein represents an initial attempt to account for the emission lines in planetary nebula. In the end, many other reactions could be envisioned, but the key aspect must remain the use of condensation reactions, as they alone can account for one-step solutions to the forbidden emission lines from ions, the emission lines from molecules, and the lack of helium-1 transitions in the UV. In this video, many aspects of accepted planetary nebula science have been addressed and demonstrated to be highly questionable. First, it is clear that the presence of forbidden transitions are not dependent on rarefied conditions. That was the lesson from the oxygen-1 aurora line observed in helium and argon atmospheres by McLennan. This conclusion was strengthened by the use of forbidden transitions in lanthanide crystals. The presence of UV-sensitive organic molecules and fullerenes in planetary nebula made any argument relative to photoionization moot. It is also unreasonable to require UV photoionization arising from a central star when the nebula can extend fractions of light years across. Clearly, the emission lines must be produced by local phenomena. Then there was the presence of rotational carbon monoxide lines indicating very low temperatures in planetary nebula on the order of 10 Kelvin, when accepted theory called for 20,000 Kelvin. The need for shock waves for the creation of temperatures well beyond 20,000 Kelvin to account for the neon 5 and argon 5 lines was also unreasonable. By contrast, a flurry of much more logical solutions was advanced to account for the emission lines of planetary nebula. These solutions are dependent on the condensed nature of the stars themselves and the exfoliation of stellar envelopes to create nebular material comprised of condensed hydrogen structures. The most important forbidden transitions could then be readily explained. These transitions arise from oxygen-3 and are likely to result from the condensation of two hydride ions from water. Then followed easily achieved explanations for the emission lines from nitrogen, carbon, sulfur, and silicon. Perhaps it was with the helium emission lines that the greatest strides were made. Using condensation reactions, it was trivial to account for the helium-2 transitions. then the lack of the helium-1 transitions in the UV could clearly be illustrated by invoking condensation reactions of hydrogen atom from the helium hydride excimer. This could also readily explain all of the observed helium-1 recombination lines and why emissions from the 2p shell to the 1s shell of helium were not observed. Chemical reactions with hydrogen and an activated helium atom to form the helium hydride excimer was responsible for that observation. It is certain that there is much to consider in this video. Still, I hope that everyone can come to understand that it is time to take bold new steps in the field of astrochemistry as it relates to planetary nebula. Well, that is all for today. So if you enjoyed the video, promote the channel, mention the videos to your friends and to your local astronomy club. Support me with a like and subscribe for more videos as we look more closely at the sun, the stars, and beyond. Scientific comments are always welcome down below, and I'll see you soon on the next video.